So today we have Vladimir Konotop, and he will talk about the universal form of one-dimensional potentials, which have spectral singularities. So whenever you are ready, Vladimir, just go ahead.
Okay, thank you, Andreas. Thank you, everybody. And thanks for this nice set of seminars, which allows to stay updated. I will talk, so here is my title of my talk, The Universal Form of One-Dimensional Potentials with Spectral Singularities. And practically the whole work I will talk today was done together with Dmitry Zizulin. He is in Itmor University in Russia now. Well, this is an outline. First, I will make a few preliminary remarks about definition and about our setting, what is interesting for us. Then I will discuss continuous Schrödinger equation, one-dimensional, necessary, sufficient conditions, and some examples. I will specify necessary and sufficient conditions later. Then I will discuss a possibility. This will be basically about existence of relation between potential and existence spectral singularities. Then I will discuss possibility to design potentials with desirable spectral singularities, again in 1D. And if I have time, I will discuss the same story, but applied for discrete Schrödinger equation. Well, first about definitions, because usually in loosely speaking mathematics, the spectral singularity is a pole of the resolvent, is the real pole of the resolvent. When this definition, from this definition can be directly related to the asymptotics of the solution of the Schrödinger operator. And this is done in this theorem proven by Weinberg quite long ago, saying that for the K0 being a spectral singularity of this problem must have a solution with this specific asymptotics. In this asymptotics, I would like to emphasize here this exponential, which corresponds to outgoing or incoming waves with respect to the potential. Well, interestingly, already at the beginning, when in parallel, probably the very first paper in physics reporting about what we now call coherent perfect absorption, but in the paper it was called resonant absorption, was published in '62 by Hapaluk. And I did not find English version of this paper. I only read it in Russian. And in that paper, since he doesn't speak about absorber or laser, he simply considers a problem of incidence of two waves and show that if slab on a slab which has absorption, and he shows that this incident waves can be completely absorbed. This is what we call today coherent perfect absorption. Since that paper, there was some more development until, let's say, a decade ago. And speaking about the one-dimensional problem, we immediately can also introduce it was done in this work, and introduce different other different, let's say, definitions of equivalent definition of spectral singularities, which are related to the transform matrix or to, let's say, to linear dependence of the Gauss functions. In this talk, I basically will refer on these two definitions, which are related to each other. And I will consider only one-dimensional case. And if solution has a right asymptotics, in the sense that it has only incoming waves from both sides or outcoming waves from the center, then I will call the solution as a spectral singularity solution or simply as a solution. Well, the questions which are we address are basically the following. So since this is quite, it seems to be a quite delicate property for the potential to have a spectral singularity, because one needs to put it exactly on the real, to manage parameters to put it exactly on the real axis. So meantime, many potentials of this kind were already known. And the question was whether these potentials share something in common, or they just accidental cases. If they share something in common, then the same question can be addressed to the solutions of this equation. So whether solutions have something in common, or they are just accidentally found interesting solution of the respective problem. Finally, again, if the answer is positive, so there is something in common, then how this can be used in order to construct potential with prescribed spectral singularities. So basically, these are questions we wanted to answer. So let's go to the statement. We consider it the problem. We consider it. I will consider the first part is a continuous one-dimensional continuous Schrödinger equation with a potential which has zero asymptotic, so it is localized, and potential is complex. So it jumps. Okay. Now we define. We say that a solution psi 0 is the spectral singularity solution if it has the following properties. It is differentiable, continuously differentiable on the real axis, and for a given k, it has for a given k, which is I call it here k naught. It has asymptotics written here, not only the solution, but also its derivatives with first and second derivatives. So that means that it must be continuously, it must have continuous derivatives on the whole axis, but second derivatives must exist far from at least from the center. Well, next, this definition corresponds to physical situations when the waves are outgoing. When k0 is more than 0, then we call it laser, and if k is less than 0, we call it coherent perfect absorber.
Frida has a question. Frida, do you want to come in, ask the question?
Yeah. Hello?
Frida? Frida, you're on mute. You're on mute, Frida.
The limit that the potential goes to 0 is at infinity. Is it only on the real axis, or?
No, it's only on the real axis. It's we discussed it's only on the real axis. Yes, this limit is only on the real axis. But I will specify, because I will formulate two theorems, and it will become clear what we mean, I guess, from that part. Well, we consider this equation on the real axis, actually. Okay, I should put here x in the R. Well, now we in order to formulate necessary condition, we need to slightly specify better the function psi 0, because only asymptotics were not enough for us to formulate it rigorously. So what we require from this function is the following: that this function psi 0 might have simple roots, might have simple zeros, but these zeros should be there should be finite number of these zeros. Since they are simple, the behavior of the function in the vicinity of this each of the zeros should be like this. So it's the first term of the expansion, and the next term should be at least asymptotically small with respect to the first one. This is for necessary condition. For sufficient conditions, it will be more restrictive. Then we introduce the intervals. Let me call these intervals good intervals, where function psi 0 is never 0 because the number of zeros is finite. So this is interval from minus infinity until first 0, then between first second 0, and this is the half infinite interval at the end. And the union of this interval, it's I to shorten the name, I will simply call it good interval. Now, in each good interval, we require that function it has at least a second derivative. Well, having this defined, we can construct a function. I will call it base function, which is w on x, which is logarithmic derivative multiplied by I. Having also these properties, one can establish the properties of this base function, which are the following. This is a continuous function on good interval. This function may have singularities in the points where function is 0, but again, let me call these singularities good singularities. Good singularities mean that the behavior of the function near the singularities is determined by this formula. And this function must have right asymptotics. Right asymptotics meaning that when k goes to infinity, this function must go to minus or plus k0. Remember, k0 will be our spectral singularity, and derivative of this function must go to 0. I see there is another equation, right? Hello?
No, I don't think there's a question. No, go on.
Okay, no, it was just written something, sorry. So this picture illustrates what I said. Don't pay attention now for this x1 large x, I will talk about them later. So these are points where function can be 0, the base function can have singularities. These are good intervals, okay? Well, now I will formulate necessary condition. Having function psi 0 is defined above. Basically, it is in C1 and has bounded second derivative in each closed subset of good interval I. Then, if this function solves the Schrodinger equation on the real axis, then the potential is bounded for in any closed subinterval of J and vanishes when x goes to infinity, modulus x goes to infinity. Also, for all points of the good interval, this potential can be represented in the following form. Okay, this is a basic representation which I will discuss during the whole my talk, and in this representation, I would like to emphasize the following. So it has 3 components. These 2 components often called Vladimir potential, and it was studied before in many papers. For an important part that here explicitly appears k naught, which will be a k naught square, which is spectral singularity. And this function, which enters in the construction of the potential U on x, satisfies the above properties. I mean, if it has singularities, the singularities are good, and it has right asymptotics. Well, I will not discuss, will not show proof of this because it's actually very simple. It's just substitution and accurate, and it is only necessary to check that everything okay in these singular points. But I would like to emphasize 2 things. First is that potential can have singularities. So potential in principle need not to be bounded or even continuous or even bounded. Second, in principle, if function is not 0 for the whole real axis, then the solution can be represented for the whole real axis. And this is in this way, this solution gives us explicitly the spectral singularity solution. What is interesting here, so I will discuss the solution a lot in the next, in the rest of my talk, but what is interesting here, important here to emphasize is that either the potential or the solution, they are defined by the only function, which is a base function.
I have a question.
Sure.
Don't you need to put some condition on the rate of decay of the potential at infinity?
At this point, no, because this is a necessary condition. I will need it for sufficient condition. Well, this states that if this function solves this equation and the conditions on the function for psi 0 were formulated above. Here it is important to put the right asymptotics for the psi 0.
I see.
Okay, so let me show now the example. And okay, what I was saying is that now only one function which is base function, defines both potential and a solution. Now, just to show you the example, which was known before us, it's a scarf 2 potential. We just wondering to get this base function for this potential. This is easily done. Interesting thing is that here, which I discuss a little bit more later, that this function is, this potential has two spectral singularities, which corresponds to k naught equal alpha and k naught equal beta. And for each of them, one can define its own base function. So this respective spectral singularity solution is obtained simply by substituting this expression or this expression into this integral. That's it. Well, now let's go into sufficient condition. We need slightly, and here comes into play this additional condition on the asymptotics. Yes, we need impose additional condition, but not on the potential. We impose it on the base function. So we now, these conditions for the base function are now more restrictive. We continue consider this function continuous and piecewise differentiable for each good interval. Then we call discontinuities at some points. This function can have discontinuities at some points, x1, x2, etc. They are finite, and we call it them allowed if they satisfy the following asymptotics. The main, the leading order is given by this. Notice that the leading order of approaching from the left and from the right hand side each zero, each singularity of base function, they must be the same. I mean, it is important that here we have I over x minus x1, and here we have also x minus x1. Now these terms are more restrictive. They are not allowed. They are not. It is not enough to claim that they are small compared to this term. It is. It must be said that they are at least not more than of order 1. Another point to mention here is that in each interval, the function in each interval where we define, for example, function base function w1, it is here, we can approach as a one point, singular point or another. In this case, we need to require that this function allows two representations, which is in the vicinity of point x1 and in the vicinity of point x2, with in principle different next order terms, but all of them are of order 1. Finally, going to asymptotic behavior, we indeed need to require that this function decays fast enough. When we say fast enough, it must decay at least as x to minus 2 when x goes to plus or minus infinity. Well, if this is defined, then we can proceed with the with the construction of the spectral singularity solution. How we do this? We consider first each good interval. now I return to this point. Let me go back just to show you this point x, some points in each interval. So far, these are constant. We also have for this function another constant defined, which is rho j, which is amplitude of this exponent. And since asymptotics of the w were defined above, we can establish asymptotics of these functions phi j. So they are listed here. This function goes to 0, and this is an interesting fact because okay, I will discuss a little bit later, because if base function is regular, the spectral singularity solution is never 0. And these are asymptotics at the plus and minus infinity, and we see that in principle amplitudes are not necessarily equal. So far, this rho j and xj are left simply as a constant. Finally, we define this spectral singularity solution as functions fj defined on each good interval. And since in this special points x1, xn, these functions go to 0, we can complete this definition by defining function phi 0, let it 0 in the point x. So now we constructed the function psi 0 on x in the which is continuous on the real axis. However, this is not enough, because if we want to be the solution, it must be also in C1. So it must also continuously differential. And this is possible to do provided the following procedure is done. And now we come to sufficient conditions. So if we consider a set of these parameters, xj, this is large x, in each interval, given, and we define some constant amplitude, which is rho 0, which is different from 0. Then we define the rest of these parameters, rho 1, rho n, by the recurrence relation, which is given here. In this recurrence relation, we have these parameters which are free in the sense they must be inside good intervals, but they are free inside this interval, they are free. And here we have two representations of the base functions which are related to approaching to the left and to the right spectral, these special points. Well, then if this is done, then it is possible to prove that the function defined as before will be continuously differentiable. Then this function, as I showed before, has right asymptotics, and this function, and for each value of x in the good interval, this function solves the Schrodinger equation with this potential. So in this sense, we got the sufficient condition. Again, if we notice that if there are no these singularities of the base functions, so if the base function is bounded on the whole real axis with right asymptotics, then this equation is, we don't need to introduce different intervals, and this u is precisely the potential which I formulated before. Now the asymptotics of this potential comes from the asymptotics which are defined by the asymptotics of the base function. Okay. Well, now let me before showing some examples, let me turn to the case so far. W was a complex function. In principle, we did not specify that it is real. If it is real, meantime, then...
Can I ask a question?
Sure.
Your W, it goes to 0 like 1 over x squared, right?
At least, yes.
So this potential is going to go like 1 over x cubed.
Yes.
But there are potentials which don't go like 1 over x cubed, and they do have spectral singularities, right?
There are potentials which
do have spectral singularities, but they go to 0 much slower than 1 over x cubed.
Well, much slower. Oh, just a second. Well, actually, this is not. This, in principle, doesn't seems to be in contradiction with what I. With what I said, because
this is not the most general potential which has spectral singularity.
Okay, let me think a little bit about this a little bit. Well, let's say the following. So we have well, probably. Can you give me an example? Maybe this would be simpler to compare this with an example.
Well, the only thing I know is that if your potential satisfies this Faddeev condition, which is like it's faster than 1 over x squared, but not 1 over.
No, but if it's faster than 1 over x squared,
yeah,
then it's okay.
Yeah, yeah.
Then this is what I said to you. This is what I showed you.
But that is W. U is W prime, so it has W squared and W prime. So that's what I was wondering.
Oh. So you mean that there are potentials which decay like 1 over x squared, which
x squared plus epsilon, say.
Well, but if plus epsilon, then probably it's okay, no?
Yeah, it is okay. I mean, but your construction is a kind of puts stronger condition, if I understand it correctly, because you say that W should go like 1 over x squared. And if W goes like 1 over x squared, then your U goes like 1 over x cubed. But maybe we can discuss it later.
Yeah, okay. So maybe if you would show example, then it will be more easy to understand what is the. Anyway, so.
We have one more question. Maybe we just ask it also now. Ken, do you want to come in and ask the question?
Okay, I wonder how you interpret the conservation of the current in this continuous wave function.
How we interpret a what?
Yeah, the conservation of the current probability.
Sorry, I did not understand. I mean, you're speaking about this?
Yeah, I mean, you have discontinuities and you are defining the conditions. I mean, the wave function is such good discontinuities, if I understand correctly.
But you have here parameters which you can adjust to for function that do not have discontinuities. You can adjust. Moreover, so this is enough. This function is continuous. So what the problem? It's verified directly. So the problem could be first derivative, but these parameters are used to ensure that first derivative is continuous.
I think there is a misunderstanding. There is no conservation of probability. These potentials are.
No, here I am not speaking about conservation of probability. This potential have another conservation. In some sense, this is a slightly different story. Maybe I should, if I succeed, come to the slide where I will show you something that I think you refer as conservation of probability. because these potentials does have a kind of conservation of probability, even in the nonlinear case, even if this equation is nonlinear. It has integral, a special integral.
Okay.
I will tell you later. Okay, but I am not speaking about conservation of probability now. Well, let me go now to the case of real potentials, which is most studied with these potentials. People mostly were interested in real base functions. Then this potential, which we constructed, has additional symmetry with the Twinian operator, which is written here, and Twinian operator defined by the base function. And then for an interesting outcome of this construction is the following: that if in addition to the spectral singularity, now we are speaking about real W, if in addition to the spectral singularity there is another spectral singularity, then necessarily this another spectral singularity will be self-dual, in the sense that if diagonal element, if M22 diagonal after some matrix is 0, then diagonal element on minus K star or M11 is 0, 2. In the sense that then it is guaranteed that both diagonal elements are 0. This comes from the properties of the transform matrix, which one derived from this additional symmetry for real W. Another interesting consequence of this is that K node is a spectral singularity, is a self-dual spectral singularity only if it is at least second order 0 of any of the diagonal matrix elements. Otherwise, it is necessarily a simple spectral singularity. Well, and here this is about this conservation law, in some sense, if I understood it correctly. Now, if we can normalize always, this is a linear problem, normalize always solutions to the non-zero equal background amplitude, equal asymptotics at plus minus infinity for both. I'm speaking about self-dual spectral singularity in the point K star. Now, it turns out that these two solutions are related to each other. And this is a conservation law which is specific for that potential. So it is, this is also straightforwardly can be checked that, that this is verified. This is also seems to be surprising property because if you think about the following, so we have a potential, we found a self-dual spectral singularity, and if we find the Lazen, we compute Lazen and absorbent solutions, and then computing them, we can establish the existence of one more spectral singularity, which was not under the consideration even, because these two the relation between these Lazen and spectral singularities and absorber solutions in spectral singularity K star, they are determined in some sense by the third spectral singularity, which was on the basis of construction of this function, spectral singularity of the potential. Finally, and this is, by the way, this is dependent on X. So if you like, this is, you can interpret this probably as conservation of the probability. And this, as I mentioned, this conservation probability also would be valid if equation would be nonlinear. Now, finally, there is another interesting property. I'm afraid I cannot see it. I don't know whether I put here. Okay. If we want to compute pumped or absorbed energy by the potential, then it is entirely given by this K naught by the spectral singularity, which was on the basis of construction of the potential. This is particularly interesting property if one wants to solve, let's say, the optimization problem requiring, let's say, minimal pumped energy to get, let's say, laser or absorber or whatever. Now, let me show you.
Farhan has a question. Sorry, Vladimir.
Sure,
Farhan,
sure.
do you want to just ask your question?
Okay, my question is related to what I asked. My question is, what is the fall-off condition for W prime?
What is the?
What is the condition for the fall-off rate of the W prime? You know, it doesn't follow from W.
Sorry, I really don't understand. Oh, W prime?
W prime, the derivative of W with respect to X.
The condition about the W prime are all here. So these are all conditions which I need.
It is on W, not W prime.
W prime, well, it is written here, continuous and piecewise differentiable. For the good interval. And in this point, you must have the following asymptotics.
Okay, so you have no condition on the rate of fall off for the potential U at infinity.
The potential U at infinity is determined by asymptotics of W.
Okay, but you need to indicate what the rate of how W prime goes to infinity.
I can do this. Well, I understand. Okay, sure. I can do this. I can do this on this basis because I know what is W through the W prime. So I
wonder how you can say do that. You know how W tends to 0 at infinity. How can you determine from this fact? How can you determine the behavior of W prime?
Behavior of W prime can be any at the infinity, which, well, it must be differentiable function, okay? But it must go to K1 or minus K1. Oh, by the way, this is probably answer to the decay of potential. Now, I think because notice that W doesn't go to 0. W goes to K naught or minus K naught, the plus infinity and minus infinity. So when we consider W square, first term here, this is to previous question. When we consider this term has leading order 1 over x squared actually, not 1 over x cubed. It behaves like 1 over x squared. It comes directly from here, as you see. Okay, this is the decaying function, but K naught is this function the W must approach very fast K naught. And when I say very fast, it's 1 over x squared, but not 0. So that's why this is does not have any contradiction with the fact. So we can construct potential which are decaying like 1 over k squared, or 1 over x squared. Okay, so I'm afraid, I'm sorry if I did not answer it completely the question, but please let us discuss maybe a little bit later after the talk. It will be my pleasure to give you all answers. I hope I can give them. Well, this is an example this is a numerical example. Okay, come on, I probably will will talk only about 1/3 of my speech. This is a numerical example shown for this function, which is real. Here we observe the following interesting phenomena. First, we have chosen this base function with k0 equal to 1 and constructed it for some value of gamma. Then this potential does this base function gives a potential which has spectral singularity. Then we start to increase gamma because we having spectral singularity at k0 does not yet mean that there is another spectral singularities which must be self-dual. Then we increase gamma, and suddenly, and we arrive at the situation for some specific gamma when appear two spectral singularities. These two spectral singularities, self-dual spectral singularities. You can observe in this spectral singularities that they have interesting properties. One of them becomes zero, amplitude of the field becomes zero. This means that it corresponds to the singular base function, while another one is a normal one, which corresponds to regular W base function. Then, of course, in this case, we also have jump of the phase. Another interesting property here is, you see, this is blue is a domain of absorption, while red is a domain of gain. So you see that laser has minimum, actually zero in absorption domain, while coherent perfect absorber instead has a higher amplitude inside the absorbent layer. One more interesting property here is that if we start increase gamma, then we get another pair of exceptional points. This point can disappear, but what is this point is not exceptional anymore. But what's interesting here is that until this point, until this gamma, system is stable. It does not have complex eigenvalues. But starting with this point, system acquires these complex eigenvalues. These complex eigenvalues, visually, if you look just at the line of complex eigenvalues, they will just split out from some point of the continuum spectrum. So this is some point in the continuum spectrum is precisely the spectral singularity. So this is a phase transition through the spectral singularity, which is in some sense which resembles, but not the same as a spectral singularity. As a spectral singularity, as phase transition through the exceptional point. Well, and continuing this process, we have another pair and self-spectral singularities. Probably there are more. We did not do much more numerics here, but here system is already unstable because it has these two eigenvalues, which are here. They are make system unstable. This solution, which I showed you, in principle, is interesting for the following reason, which we weren't we didn't explore fully. But if you look, you think about this as about solution of the Schrodinger equation, time-dependent Schrodinger equation, or wave equation, then the solution, which includes evolution variable like time or propagation distance in optics, would look like this. Now, and these are asymptotics of W. Now, if you think that about this k0 on the real axis, then here we have laser, here we have coherent perfect absorber. But now, if you go to complex plane, which I'm speaking about k0, not about x, we still consider problem on the real axis. Then this solution still have physical meaning, and if the imaginary this is line when imaginary k0 is 0, and if imaginary part of the solution is not very high, then this is what people in optics called bound states in continuum. These are not really bound states in continuum because the spectrum is not really real, but the real part of the spectrum is in the continuum spectrum. This means that this is a solution which is propagating and growing at the same time. If we increase the imaginary part of k0, and we are here, well, from this side we have the same but decaying solution, and we have k0 here. This solution will describe a bound state which is not moving, but it is still growing or decaying. Finally, if we are on the real axis, then we simply have a bound state for this given energy ik naught. So this means that this procedure in some sense could be used in order to construct potentials with a desirable eigenvalue state, or with a desirable growing or quasi-bound states in continuum, and even in order to construct potentials with exceptional points. Here is an example. In order to construct potential with exceptional point, it is not enough only to fix k0, which now must be imaginary, but one needs to have some freedom with parameters in order to manage, in order to deform this potential, because we need two eigenvalues to collide. So this is an example. If you consider this base function, then the problem is solved exactly analytically. So one finds the psi naught. This is solution corresponding to this base function. This is a localized solution now because of this k naught. Then one can compute this integral explicitly of the psi naught square and verify that this solution is self-orthogonal if Zn is Zn is this half integer value. So in this way, we return to one of the examples which were also studied before, but of course this was done analytically, but one of course can consider here different functions, any function actually, with only requirement have right asymptotics. And then the solution will not be possible analytically, but we don't need to do it numerically. Okay, since I think I'm close to the end of my time, let me probably I will not speak about discrete system, but I will show you how this can be used if you want to construct spectral singularity potential to construct given spectral singularities. First, if you want to have one single singularity, this is very simple. Just choose any W on X and explore any shape of W on X with the right asymptotics, and you will get different potentials and choose one you want. Now, suppose that we want to construct potential with n spectral singularities. Then we, for each of them, we must have its own base function. So there must exist different base functions, right? With right asymptotics. Then each base functions will determine the spectral singularity solution. Then each of these base functions will define the potential. But this is the same potential for all of them. So there is a relation between these base functions. So, for example, base function which corresponds to j plus 1 singularity must satisfy this equation involving base functions with j with singularity j with kj. This problem actually is easily solved because it can be solved in this way. Now, if define just difference, I call it generating function. Obviously, for this generating function, we need to impose some conditions because we cannot violate the conditions imposed on the base functions. And these conditions are written here. As soon as this function is given, one can construct W base functions from these equations and these definitions. So here is a result. This is very simple. Now, this is an algorithm. Choose any chi1 which must have no zeros or must have allowed zeros or allowed singularity. I will specify this in a minute, which is differentiable everywhere except allowed, disallowed singularities, and which has asymptotics which are defined by K1 and K2. Having this function, obtain two base functions, W1 and W2, use any one to get U, and use both of them in order to obtain the respective, I should put here psi1 and psi2 spectral singularity solution. What is allowed zeros? So if you look at this, let me go back at this equation, we need this function to be good. Okay, so we cannot have, we are allowed to have, let's see here, singularities, but only those which I defined in the definition of the base function. And this is done if chi1 has the following property, that if in the point where this function 0, the derivative of this function is either this or this. In one case, it is simply removable. In another case, and then base functions are regular. In another case, base functions are singular, but singularity is allowed. Finally, what is allowed singularity is a singularity of this type, which is the type of the singularity for the base function. So any functions chi1 which satisfies this condition will allow construct potential with two K1 and K2 spectral singularities. Here is an example. I will do fast a little bit. This is an example. We just took this an example. You see if A1 is 0, we get a PT potential, which is shown here. Now U is explicitly can be written, actually not only here, but U can explicitly written through the generating function, not through the base function. But if we substitute this equation, it will be horrible expression. Although the shape of the potential is not so awful, so it looks quite regular. And this example of the same spectral singularities, but with a potential which is non-PT symmetric. Here A1 is different. This choice is somehow arbitrary. Well, then this is an example of these two spectral singularities, but let me show you this example where chi1 has is by itself singular at x equal to 0. Respectively, we have singularity of the base function, and notice here that respective solution which corresponds to this singular base function has 0, while another solution does not have 0. These are two solutions corresponding to these two spectral singularities. Okay. Now, another technique which can be used here is a kind of colliding spectral singularity. And may I have 3-4 minutes more, at least, to finish this second part?
Sure, go on, go ahead.
This is a formula which was written before several times when I wrote through when W base function was written through the generating function K1. The only thing I added here explicitly K1 and K2. Now, if we find K1 and K2 satisfying these conditions, okay, then we can have limits, good limits, when K2 goes to K1 and have a limiting base function. Limiting base function will be then explicitly written through this generating function, and the potential will still have the same form, but base function here is this limiting base function, and K1 is the spectral singularities of the second order. Now, okay, here is an example, but probably this shows how diagonal element behaves here. It doesn't cross but because this is second order zero, so it stays positive. But then let me go to 3 spectral singularities. I will do it fast, and probably this next couple of slides I will finish. When one has want to construct potential with 3 spectral singularities, it is not enough to compare only 2 equations. One needs to compare 3 equations for the base functions. If we use generating functions, we may have only 2 generating functions. So, but we need now to solve these 2 equations. Okay, these equations still can be solved. To solve them, we use these ansatz, introduce a new function, new one. And if you look at this expression is obtained as equation for new one. But don't look at as equation for new one, look at as equation for chi1. Because for chi1, this is simply a squared equation. I should emphasize this too. So this is simply binomial, this is simply a quadratic equation for chi1. This means the following. If we choose a new one, then from this quadratic equation, we can obtain chi1. From chi1, from this expression, we can construct chi2. From link between w and chi, we can construct 3 base functions. And finally, we can go, as soon as we have a base function, we have potential, for which we can use all of them, and psi naught. The problem, however, is that not any choice guarantees that psi1 is continuous and regular. So remember, we imposed several conditions for this to be meaningful mathematically. We do not have solution in general saying that this can be solved. How this can be solved algorithmically, let's say, but it wasn't too difficult to find right way example. To find right example, new one which satisfies, which gives good condition for chi1. This is an example one. K1, K2, and K3 are spectral singularities, which in this example are shown by points 1, 2, and 3. And that is simply a parameter which is found by adjusting, by satisfying the above requirement of regularity chi1. Don't be afraid, I will not go too much. I just go to n more or less 4, and I will not go too far, because now we have, following that procedure, we now have not 1 condition for new one, but we have 2 conditions, because we added 1 more equation. And this problem we actually were not able to solve. It remains unsolved. We even could not find any reasonable example. And my feeling is that this situation with this procedure constructing more singularities, 1, 2, 3, 4, etc., is very similar to what happens with the zeros of the polynomial. So we know how to find first order, zeros first order, second, third, fourth order, but then we do not have an analytic formula to find zeros of the polynomial. If we are lucky, this can be achieved. So if we impose some symmetries, probably we can reduce this number equation and solve them. Okay, probably I should stop here and escape discrete part, but just only one remark. The discrete part of the Schrodinger equation allows to repeat almost entirely the procedure developed for the continuum Schrodinger equation. The only difference now is that well, not only, but the difference now is that the base function is a relation between potential and base function is now more tricky. It is written here. This is the base function and this is potential, and the rest is can be done completely, but even in some sense even easier than in continuum case, because we do not have problems here. We only need problems with the convergence of the sum. So these are easier than doing this at singularities. Well, I'm sorry, I have to drop everything, and just let me show you why discrete system was particularly interesting, because this is experiment where this experiment was done in Kaiserslautern. I was participating in this in the laboratory of Herwig. And this is an experiment where coherent perfect absorber was observed for matter waves. So this is a Bose-Einstein condensate in the central, placed in the optical lattice. So this is a discrete system. In the central part, in the central side, the condensate is illuminated by electronic beam. So in this picture, you see how dissipation rate of the atoms, how this condensate loses atoms when intensity of the beam increases. We should go from this side to this side because this is this is okay. This is right. So we see here clearly two regimes. One regime is when although we have this dissipation, the condensate practically does not lose atoms. Okay, and then we and then we have another regime. This is a regime of coherent perfect absorption. This is this you can see an image of this regime. This is a regime where eliminating of atoms from the central side is exactly compensated by the velocity, by the by the incoming flows from both sides to this center. And this is an image of the usual dissipative regime, where when this balance is not satisfied anymore. Also, these discrete systems, as I showed very rapidly, another picture could have specific optical applications for arrays of optical waveguides. That's why we also developed this also for discrete system. So these are basically part which I talked to you. This is part which I did not have time to talk to you, but this is a very brief summary telling that almost all known for continuum model can be put for a discrete model too. And also I referred how in some cases we could construct multiple and high order spectral singularities. So thank you very much.
Thank you very much, Vladimir. Do we have questions?
I have a question. Well, I couldn't see if you can apply this procedure for finding finite range potentials.
Yes, we can. Of course. Please notice that this U is not need not to be differentiable. I put it here. Wrote it. It has singularities and it need not to be continuous. Yes. For example, in the paper where this is done, we specifically considered example for the step for the rectangular potential. Yes. Actually, it is not as difficult because base function is something like tangent or secant or sine, something quite simple. Yes, we can. Okay. Well, moreover, we can you can apply it for delta potential. For delta potential, base function is a Heaviside function. In some sense, we try to consider more well-known examples to illustrate how it works. Because for unknown examples, we just take. I don't know whether it's a question or.
Any more questions?
Well, if there are no more questions, I have a general comment. This is Philip Mannheim. Alas and alack, I've now started teaching on Thursday mornings at exactly the same time as this seminar series. And I've just managed to come in at the very end after I finished teaching. So I won't be able to be an active participant for much of the rest of the series. And so I just wanted to say how much I've appreciated the series that I've been able to follow. And I'm very much indebted to Andreas and to Francisco for having put everything together. And I'm only sorry that I may not be able to join you much in the future, but we will have some vacations.
Thank you, Philip. Any more questions related to the talk?
May I have a question?
Yes.
What about systems of Schrodinger equations?
About systems?
Yes.
Excuse me, about what systems?
Pardon?
Maybe I do not have a good connection. Could you please repeat? What about?
You made this construction based on continuous Schrödinger equation.
Yes.
And moving to W, you get this conversion of to Riccati and then
Yes.
So something like that was done in supersymmetrical quantum mechanics, where there is natural generalization to systems of Schrödinger equations where you have matrices.
Yes, this is very similar. I understand this, and actually, there are more studies also related to obtaining PT symmetric system potentials with real spectrum and with linear case. Yes, what you say, this is right. Our basic probably difference of what is considered here is this asymptotic behavior, because what we are interested in a solution having special asymptotic either only outgoing or incoming waves towards the potential. This potential, I think I mentioned it in the talk, this potential which I showed you without K naught, especially with real W, was considered a lot, and sometimes it's called Vadati potential, because Vadati use it for applying theory inverse scattering technique, showing that this potential may give spectrum with pure real spectrum. Yes, this is true, but I don't think it is. It's overlap more than just a general form of the potential. So basically, my message is that this general form will be for any spectral singularity. So potential, which if you have potential with spectral singularity, it will have this form, and solution will have this form.
Okay.
Okay. Everywhere except maybe points where this W itself is singular.
So thanks.
Any more questions? Farhang has a question.
Sure.
In fact, I'm really interested in the construction because it seems that you only need to have some special asymptotics on W. I have written an example for W that satisfies this condition. The follow-up is 1 over x4 up to a constant. Okay, but W prime is not bounded. And that means that the potential U is not bounded.
Yes, potential U. Well, if you are speaking about some specific function, specific potential, better to have a look at it. But I wrote here that U may be not bounded. U in principle is allowed to have singularities. These singularities cannot be very strong, and this is achieved by these conditions which are imposed for W. If you look at this condition, which is written here, and you look at this formula, then you see that the leading order of singularity will be cancelled here. So it will not be as strong as 1 over x minus g squared. So
no, I'm mainly interested in the asymptotics of U. Okay. For example, if you consider, if you suppose that W is sinus of x4, over x, sinus of x, x to the 6 over x to the 4. Okay.
Sorry, sine x.
I have written it in the chat.
Okay. Sine x4 over
x6. Then the potential would not be bounded.
Yes.
But your construction works, and that's interesting.
In principle, I think this is what I try to. The construction. No, by the way, this function, this double function is good, no? Because you have sine x to 6 divided sine x to 4. So
but its derivative is not.
Sorry?
Its derivative is not.
Derivative is not.
Yeah.
Okay, but it must be piecewise derivative. This function is, what is done is, it is imposed here that it must be, where is it? It must be piecewise differentiable.
It is. I mean, this is piecewise differentiable for x large, but
yes, okay.
Derivative, it blows up. So it doesn't go to 0 in infinity. So your potential will blow up at infinity.
Yes, but well, this goes to constant, right? At infinity.
Oh, this goes to constant at infinity, but its derivative will blow up. You see, this is W, right?
Right, yes.
So when you calculate your potential, you're going to take the derivative.
No, but it says that it must be piecewise differentiable for all good intervals, including infinity, the semi-infinite interval.
But this is piecewise differentiable. I mean,
not at the infinity. It's only not at the infinity.
I mean,
we need good behavior until the infinity. This G, this is a semi-infinite interval. So it must be good in the whole this interval.
It is good there. I mean, this is even analytic.
Well, okay. Let us to be completely rigorous. Let's do the following. We need to see here on sine squared x to 6 over x to 8 real minus I, so they don't cancel. Okay, maybe can I send answer? Not right now, because I want to check it.
I think that might be best. Yeah.
Yes.
If you continue this discussion outside. Yeah.
Yes, I think it might be best, because I must say that when these transparencies have slightly reduced formulation, but let me clarify this. Can I send you a message then with this? Farhan. I see.
Maybe we should talk to each other via Skype or email.
Sure, of course. Let's do it. Let me give a better look on this potential.
Okay. Are there any other questions? Then let's thank Vladimir again. Yeah. Thank you very much, Vladimir. Yeah. Thank you.
Thank you. Thank you, everybody. How can we connect to each other? I don't know. Okay,
Email, I suggest.
email, or I can put my, probably I can find in the list of participant emails, right?
Yes.
Okay. Okay. Please, if I don't find, and you could send me, probably I should write my email. This would be